Greetings, everyone. Y'all there? Someone there? Can someone speak up at home because I'm not hearing anyone right now?
We hear you.
Okay, perfect. Thank you.
Mhm.
Let me share the screen. Okay, so we are in our second of 4-day lecture on functional languages, and today I'm going to go over the syntax for scheme, and then I hope to be able to go over the creation of functional programs. If I don't get that far, that's fine, because there is not a lot to speak about as far as functional languages and evaluation orders. So the big order of the day today is getting you used to using Scheme, comfortable using Scheme. And then we have time to show you the two different techniques that I've come up with, that, or I think, I shouldn't say I've come up with, but I think are good. Whoops, but that's not it. There we go. Basically, there's two different ways that I think are good templates to use when you're creating a functional program. One is using tail recursion, and one is using an inductive construction. I'm going to go over 3 different examples to show you how you might be able to do that. It is getting toward the end of the semester, so I have not turned my attention yet to the final exam, but I will be doing so over the weekend. The exam is where are we? That's 465, sorry. There we go. So the exam is going to be a week from, well, 2 weeks from tomorrow. And you can see it's kind of late in the afternoon, 3:30 to 5:30. If you want to take it in person, I will be here and you can take it in person. You can also take it via Zoom. It's more likely to be less coding and more multiple choice / multiple answer this time. But as I said, I haven't really turned my mind to it yet and won't until this weekend. So I'll give you more details about the exam next Tuesday when I have a better idea what's going on. I can tell you that the sample exam is a pretty good one to look at as far as giving you an idea of what to expect. And I believe I have a review guide that I'll be able to publish for the final as well.
I have a question regarding t-invoice.
Yes, go ahead.
Is that 30 points applied to like the lowest homework or to all homeworks?
No, it's just added. So the question is, how is the 10 voice extra credit handled? I just add 30 points to your cumulative homework grade. So it's, if you had a perfect 1,000, because there's, I'm sorry, 9, there's 9 assignments. So if you had a perfect 900, you'd now have 930 out of 900.
Awesome, thank you.
And you can get over 100% on the homework assignment. So it's definitely the best place to apply it, I've found. Other questions? Okay. In that case, let's move on and start talking about Scheme and some of the also things that can drive you crazy about Scheme that I'd like to highlight. So I have this nice little, almost like tutorial, and I thought maybe I'd let you go through and work the tutorial, but I realized that there were some things that you can easily go wrong, and it'd probably be better to just go over them. So I shall do so. Again, you can get to the command line interpreter for our version of Scheme, which is Gambit, with the command GSI on the Hydra machines, and that will put you in a command line interpreter. You can define global variables with define, but unless I tell you otherwise, the only reason you're allowed to use define in this course is to assign a name to a lambda function. So I don't want you using global variables in this course. And that's what define does. It defines essentially a global variable. So I'm fine with Gambit, and Scheme doesn't have a good way to assign a name to a function. It just has the lambda constructor for a function. So I'm fine with you saying define a name and then giving it a lambda expression as the value. The more common way that you assign a variable a value is with a let statement. And the way a let statement works is as follows. So a let statement starts with parentheses. Then it has variable declaration list. And then it has one or more expressions. So it acts, and then it has a final parentheses. So it's effectively a list where the first element is let, the second element is a sublist consisting of variable declarations, and then the remaining is a variable length list with expressions. The value of the let is whatever the last expression evaluates to. And the variable declaration list is a collection of pairs. So variable one, an expression that's to be assigned to it, variable two, an expression to be assigned to it, and so on and so forth. Okay, so let, much like a block in a imperative language, but you got to be careful with let statements. So let's say that what you want to do is, let's log in. Say I want to say let A be 10. And now you want B to be plus A 20. Okay, which seems normal. And then I'm going to return plus A and B. And I get error, unbound variable A. The issue is that Lisp thinks it should be able to evaluate all variable declarations in a let list in parallel. So, or in particular, in any order it pleases. So while it may look to you like this 10 should be assigned to A first, and therefore when we get to this expression, A is 10 and therefore B should be assigned 30, that's not the way Scheme sees it. Scheme says I can evaluate them in any order that I want. So if you want to force Scheme to evaluate them sequentially, use a let star. Now you can later variables can depend on earlier variables for their binding. And I got 40. So if you don't care about the order in which your variables are bound, which is often good because Lisp can optimize it if you don't care, just use a regular let. But if you want to have the bindings be executed in sequential order, use a let star to do it. Okay. So comments in Lisp, or in our version of Lisp, they are starting with a semicolon, and anything after that is a comment for that line. Statements do not end with a semicolon in Scheme. They end with a right parentheses. So that is the delimiter that does the end of it. Printing stuff is not an easy thing to do in Scheme. So the display statement prints one string, and that's all you get is one string. So if you want to display multiple results like here, you actually have to write multiple display statements, which is a pain in the neck. And then if you want a new line character, you specifically have to call the new line function to get a new line to print out. So fortunately, in this course, we're not going to be particular about formatted output because the printing capabilities are pretty rudimentary. Okay, so that's pretty much it. You can display one expression. Basically, what goes here is an expression after the display, and you get one thing. So you can try it. You can say, okay, let me display two things, and you get an error message. Okay, and notice display 3. It worked just fine. It printed a 3, but it did not print a new line character. So if I had wanted, I would have had to do it like that. Now you'll notice the 2 here at the prompt and the 1 up here, and there was nothing here. It means I'm actually too deep in errors. So if I want to return back to the main prompt and pop off my errors, the comma T will do the trick, get me back to the top level prompt. So for debugging, Gambit does have a bunch of debugging commands. I must admit, I don't really use them. The only thing I have found to be particularly useful is the trace function name. And that will trace things. So for example, let's say I define a factorial function. So I'm going to define a factorial function to be lambda n. Let's see. I know that you haven't seen all of these conditional stuff yet, so don't worry that we will get to it. Okay, so what I did was define a factorial function. I said if n is 0, return 1. If n is 1, return 1. Otherwise, return the result of multiplying n by the factorial of n minus 1. So if I say fact5, it works. I can say trace function fact. Didn't like that. Trace. So now if I run it, it gives me some output. So it says that factorial 5 called factorial 4, which called factorial 3, which called factorial 2, which called factorial 1. Factorial 1 returned 1. Factorial 2 returned 2. Factorial 3 returned 6. Factorial 4. So it can give you an idea of what your function calls look like. And I know this was simple, but as we get more complicated, I'll show you how the trace function can be useful for debugging. Okay. Division. List supports rational numbers, so that if integer division does not result in an integer result, it actually returns a rational number, a fraction. I can force it by adding now it will evaluate to a floating point because I forced it with a period there. But otherwise, integer division results either in a quotient if it can evenly divide it, otherwise it ends in a rational number. And for the most part, you are going to be writing files and then loading them. So use the SCM for scheme suffix. And once you've loaded it, it executes whatever is in that file. So typically it would be just a function, but let's take my trace function, my factorial function, and let's put it into fact.scm and write it. Now I can load fact.scm, and I'm not in the right directory. Okay, let's get out of here, re-enter. Okay, so it loaded it. Now I could say fact5, and it works. Okay, I could also, if I want it, I could have put a display statement in there. Display statement there. Ill place defined. That's because I wanted display. Sorry. No. Really wasn't ill-defined. Now let's display fact5 and a new line. We load it. Not liking that. Why not? Display, because I didn't make it into, didn't call it. There we go. So now I'm calling it, displaying it. There you go. So it actually executes what's ever there. So that actually printed out 120. Okay. And every time you load qsort SCM, it reevaluates what's ever in there. So you don't have to shut down the interpreter if something's wrong. You could actually go into the file, edit it, and reload it, which in a big project is actually kind of nice. If you have a system that's running, you could actually start it at the command line and let the system start running. And if something goes wrong, you don't have to shut down the system. You can actually dynamically fix the system by going in and fixing whatever function is creating a problem, reloading the file with that function, and then starting things from wherever the error had occurred. So when you see sometimes, okay, so that's divide by 0, and I'm in here. I could actually do something to fix that problem. Let's say that I had said something like, to make it awful, I'm not letting you do this, but I say define A to be divided 60. Okay, it causes an error, but now I could redefine it, a to be, okay, divided 62. Okay, I know it's a global variable. Now I come back to the main level and a is 3, and I could start up my running from here. So I can fix things on the fly without shutting things down, which is nice if you have a big complicated system. Let's say it was a system monitoring a nuclear power plant. You don't want to shut down the monitoring system. So you want it to keep running and be able to fix things on the fly. So you can do that with Lisp. Okay, so Lisp supports the usual set of data types. With Booleans, the value for true is #T, and for false is #F. Okay, those are the defined constants for true and false. Strings are enclosed in double quotes. Unlike in scripting languages, it may look like putting something in single quotes is creating a string, but it's not. It turns out that putting a quote, a single quote in front of something turns it into a symbol as with the value of whatever follows that quote. So in fact, you would not be creating a string Brad, but instead a symbol with the name Brad and a single quote. So don't use single quotes, so it gets you in trouble. And characters are the same thing. If you say, you might think that's the character C, but it's not. It is, or it should not be. It's supposed to be the symbol C and a single quote. We're not going to deal with characters, but like to get the character A, you would actually have to say #/A, kind of a pain in the neck, and we won't be dealing with characters in this course. So sometimes what you want to do is actually store a symbolic reference to a parameter. You'd like to be able to say something like, let A be 10 and B be A. Okay, and then you can force an evaluation of B later. Ways that, so if we say plus E and A, I'm not sure this is going to work. It doesn't. But basically, just like Lisp doesn't have pointers, but in some sense, when you say B is equal to the symbol A, you're going to be setting it up so that there's a way to force the evaluation of B, and when it evaluates, it will evaluate to the value of A. So it's kind of like a pointer in some sense. You're saying B is whatever A is at that moment in time. Okay. Okay, so then those are the basic types: numbers, strings, Booleans, symbols, and characters. Then the one built-in data type is a list, which you've already seen. So you can create it with the list command. But you can also shorthand put a single quote and create a list like that as well. Now, the difference between the two is that list will evaluate any expression. So if I say list plus 20, 30 minus 10, 5, you get the list 50 and 5. If I instead say it like this, I get the list that consists of this value and this value. So it's not evaluating them.
I have a question.
Yes, go ahead.
Is there any reason to use cons over list if you only want to make two? So like if you have like the first, so cons prepends an element onto the front of a list, right? Or
Right.
onto the front of
Yeah.
anything.
Yes.
Okay.
So, yeah, so cons, okay, so we'll get to cons, but here I can just, yes, so cons like that just creates what's called a con cell with two elements, which you sometimes do when you just want to return something with two values. But normally you're using cons in conjunction with a list. So as you said, normally you're using it to prepend something to a list. So you might say cons 6, 3, 6, 8, and it's putting it onto the front of the list. And you'll see in a moment when we get to it, you can get what are called ill-formed cons lists. So you have to be careful about that. So let me get to that in a moment.
Okay, I didn't know if you'd spoken about cons or not.
Not yet. In fact, that's the next thing. So in fact, cons lists are created from what are called con cells. So a con cell is a tuple, consists of two values, a first value and a second value. So a cons, just like you see here, it's a pair. It's like a tuple in Python, two values. And in fact, you can get at those two values. So with the car and the cooter. So cons 3, 6 gives me 3. Cooter gives me the second value. So I can get the first value with car. I can get the second value with cooter. We'll see why in a moment they're named that way. So with lists, the way lists are created is from a con cell where the first element in the cons is a pointer to the list value. So in this case, 3. And then the second element in the cons is a pointer to the remainder of the list. So lists are created from con cells with the value being, in effect, it's like saying, list is like saying, okay, I have in C a struct where the first value, I have the thing, the first element is a value, and the second value is a next pointer. That effectively is how Lisp is constructing its lists. Okay. And this is what I was talking about by something like 6.8 can look like, okay, that's a two-element list. It's not. That's called an improper list. It's really a tuple. And a proper list always ends with an empty list at the end. So in Scheme, there's no null value, but there is that. The null value is essentially the empty list in Scheme. And the way you denote an empty list is with a single quote and then a pair of empty parentheses. So I could make, this would be, in fact, a proper list. A list consisting of one element, 3. So there are basic list operations. You just saw one. If you want to add something to the front of a list, use cons. So if I already have this list 3, so I'm going to define A to be cons 3. So I have this list A, and now if I cons 6 onto A, I get 6, 3. So that adds, and it's not in place. That's a copy. So A is still 3. And then if I want to append things, append will append to the end of a list, and it will actually merge lists together. So the append command is used to merge multiple lists into one list. And then, like I said, the way to get the first element of a con cell or the first element of a list is with the function car. The way to get the second element of a con cell, and hence the rest of a list, is with the command cdr. And these come from assembly language instructions in the original Lisp interpreter. So originally, the first element in a cons pair was held in a register named contents of address register, hence car. And the second element of a cons was held in the contents of decrement register, hence cdr. So that's where those terms come from. In regular scheme, it defines functions like first, second, and third as mnemonic ways of grabbing the first, second, and third elements of a list. But for some reason, Gambit doesn't support those commands, which is too bad. So, of course, you can always define your own first command, but I'll show you how later. You can put together, however, combinations of things. So, okay, so here's an example, first of all. So car of 8, 10, and 15 produces 8. The cdr of it produces the list 10 and 15, the rest of the list. If I try to take the car of a empty list, I get an error because it's empty. Same thing with the cdr of an empty list. Here, I can take the cdr of a single element list, and that returns the empty list. Okay, and these two will get me error messages because they don't exist. However, there are some shorthands also for getting the second element of the list. So catr returns the second element of a list. If I have, let's say, catr of the list 3, 6, 8, I get 6. If I take the catr, I get 8, because this catr actually breaks down as car of cdr of cdr. It's just an abbreviation for that. So car of the cdr, that's what that stands for. Gives you the third element. Okay, and again, the nil value is not defined. It effectively is the empty list. Okay, an important command that you will often use is list to determine whether something is a list or not. So if we look at whether this con cell is a list, it's not. But if I say list cons 3 with cons 6 and the empty list, now it's happy because I have a proper list. So a proper list ends with a nil. Now, there are some nice functions that allow you to find values in a list. And they are memq, memv, and member, respectively. And they each use a different equality comparison function. So in Lisp, there is a function called EQ, question mark, which basically does shallow pointer comparison. There is EQV, which we'll talk about in a moment, and there's equal, which does a deep comparison. So for example, if I say let A be Brad and B also be Brad, and I compare them using the equal operator, this should return false. Something is wrong. Let's do it again. Let A be Brad, B be Brad. I left off the quote. And I compare them. And this is doing a shallow comparison. And I see they're false because those A and B were assigned different instances of constant Brad. And therefore, the pointer comparison didn't work. Now, if I say equal, it returns true because it's doing a deep comparison. So normally, I recommend you use member when you're trying to find something in a list. That's the safest, even though it's slower. And it will do a deep comparison. So for example, if I say equal of list 3, list 4, 5, 6, and list 3, list 4, 5, 6, it says it's true because it does a deep comparison of all elements. Basically walks through the con cells and does a comparison on all atoms. So that gives you find. Then there's kind of the equivalent of hash tables, but I don't think that they're actually represented as hash tables in Lisp. I think it's actually just they're called association lists. They look like hash tables, but I think it's a order n linear search. So you define each on an association list, it looks like a key value pair. So it's a list of so-called key value pairs. And then when you call the assoc command with the key, if that pair exists, it returns that pair. And again, I suggest you use assoc because it uses the equal function, but ASSQ will use EQ star, so that will be the faster pointer comparison. And this one you should never use. Okay, so essentially, this is a bit like a lookup in a hash table. And it returns the key value pair. Otherwise, if it doesn't, so let's do this define. And do an associative search for foo, and we get back false. It doesn't exist. But if it does, then we get back that pair. Okay. Then some useful functions that you may sometimes, again, use. String to ask if something is a string. Pair will tell you whether it's a con cell to distinguish it from a list. And this is another thing you'll often want to know if you have an empty list. So you'll often use this null question mark to find out when you have an empty list. Because that often is your base case in recursion. It's when you have an empty list. Okay, so Lisp uses dynamic typing, so you can assign anything you want to a variable. We've already talked about the fact that let doesn't allow this type of assignment. You have to use let star instead. Normally in a let statement, you would have only one statement after the bindings because that would be the result. So normally what you do is that you have a let assemble the parts of a computation. So the way functional programming normally goes is you have a let, you get your variables, you do some computation to get each of your variables. And then you have one statement in your let, which is normally some kind of recursive function call with variable 1, variable 2, to variable n. So this is the normal way you would set up a let, with doing all your computations for your individual variables in the binding section, and then one statement that calls a function, and that's the return value. Really, the only common exception to that case is when you have to display the result, and then display is executed sequentially. So the statements here are executed in order. So this one's executed first, then this one, then this one. And typically it's only when you're displaying stuff that you have multiple statements in a let. Otherwise, you do it the way I just showed you. Okay, and I already told you, if you want to force sequential evaluation of the binding so that a later binding can depend on an earlier binding, use let star. Okay. Comparison operations. We have the normal, except we no longer have equal equal, because equal is not an assignment statement in Gambit. So you use a single equal sign for comparison. You do not have not equals. If you want to ask if two things are not equal, you have to use the not Boolean operator. And if you want to do string comparison, then there are the various, you have to put a string in front of the comparison and a question mark after it. So notice there's still the equal sign with string before and question mark after, a single less than string before, question mark after. Same idea with there's no string not equal, you have to use the not function. Okay, now, my recommendation in this course for doing equality comparison between objects, so these are fast equals for strings and numbers, okay? But if you're comparing like lists or con cells or the like, I suggest in general you use the equal command because it will do a deep comparison. And if the two structures are exactly the same, it will return true. Whereas EQ question mark just returns a shallow comparison using pointers. EQV does shallow comparison, but is supposed to return true if the elements have the same length and same value. So for example, EQV is supposed to return true with the string Brad, but Gambit doesn't accept that definition right here. Our scheme interpreter does not seem to accept this definition of EQV, and that's why, at least for Gambit, I've never figured out exactly what EQV question mark does. Hence, don't use it. Use either EQ star if you want shallow pointer comparison, or use equal question mark if you want a deep comparison. Then your Boolean operators are and, or, and not, and you write them out like that. Okay, and for grins, let's see if it does conditional things. So we know that 3 is not equal to 0. Let's say if it's going to divide, notice it worked. It looks like it's short-circuiting the evaluation. So in the first case, it looks like it found that 3 was not equal to 0, and since that was false, there was no reason to evaluate the second expression. So it does short-circuit evaluation. Okay, conditionals. Very simple. If you have a simple if-else, it's a list of 4 elements: the if statement, your comparison operation, the expression to evaluate if it's true, the expression to evaluate if it's false. If you want something more complicated, you have to use a let to do the computation, just like you would in C, C++, and Java where you'd use curly braces if you had something more complicated than one statement. Now, one thing where Lisp is very nice is you don't get into a lot of if-else statements. If you have a multiple compound statement, you introduce it with the cond keyword for conditional. And then that is followed by a succession of pairs, which are a condition, and if it's true, the value. Okay, so the way cond works is it is a condition value expression. Condition 2, value expression. Condition N, value expression N. And whichever they're evaluated sequentially, whichever condition evaluates to true first is the value returned. If at the end you want a unconditional value returned, you may use else, or you can say T, either one. And that will, if all else fails, it will return that value. So here we're asking, is the grade less than 100 and greater than equal 90? If so, we return an A. Otherwise, we're asking, is the grade greater than 80? Because if we got here, we know that the grade is less than 90, okay? Because if it was between 90 and 100, we would have evaluated there. So if we get here, we're allowed to simply ask, is the grade greater than 80? Here, is the grade greater than 70? Else, that's rather charitable, they get a B. So questions about cond. By the way, same thing here. If you want something more complicated than a simple expression, use a let. Okay, so you will often see this as the evaluation function for a let. Okay, that you saw it when I did coming back here to the factorial function. I used a cond. Now I didn't use it very artfully. What I should have done was done some indenting so that it was a lot easier to see what was going on. But this is what I was doing. My factorial function was essentially just a cond statement. Okay, functions. Functions are constructed using the lambda operator. They are followed by an argument list and then some expression. Usually, if it's more complicated than a single statement, you would have a let here so that you could do a more complicated function. And notice this is unnamed. So this is where I allow you to use define to associate a lambda created function with a symbol. So this is the one time I do allow you to use the define statement. There is no return value or return statement. I'm sorry, there's no return statement. The last expression evaluated in the lambda is the return value. So you are allowed to have multiple expressions in a lambda function. Again, it's unusual, but if you do have multiple expressions, the last one evaluate it, the value it returns is the value returned by the function. Okay, parameter passing is by reference. So if you modify a list, it will be modified when it returns to the calling function. And something very important, if you want to define a recursive function in a let binding, which you will often want to do, you have to declare it as let rec. So you've seen let star. If you are declaring a recursive function in your binding list, you need let rec. If you want it to be order to matter, you have to say let rec star. So here I'm creating a recursive function, fact, and down here it's calling it recursively. So if I don't have a let rec, I will get an error message. So here I declare this recursive function in my let statement, and then my one statement that actually evaluates is a call to factorial. That is your essentially 45-minute introduction to Scheme. These are all that you need for the homework assignment. So we're not going to concern ourselves with file IO. Any input you get will be presented as arguments to a function. So basically on the homework, you're creating a number of functions, and our test data will be to simply call your function with some arguments that we're passing in. If you need to print something, you will do it with the display statement. You'll notice I did not provide you with a single imperative statement, so you are not allowed to use any imperative statements like set in your code. You have to confine yourself to side effect-free programming. Okay, so questions thus far?
So one of the questions on the homework has, so are we literally passing in a function as a parameter to filter?
Yes, you are literally passing in a parameter, a function as an argument to filter.
Okay, so, and
Go ahead.
we can just literally apply it to elements of the second one? Is that how that should work?
Yes. Mm-hmm.
Okay.
That is. So we'll get to that when I cover higher order functions. I guess we'll get to that. So, but
Okay.
yeah, you got it exactly right.
Okay,
That's
cool.
what filter is doing. Okay, but that's still a little beyond where I am at this moment. So the next thing I wanted to do was show you some some ways to create functions using Scheme. So I want to walk through a few of them. Okay, so what I want to do is show you what I consider basic techniques for constructing functions in Scheme. And I don't care which technique you use on the homework assignment unless I specifically tell you use one approach or the other. Okay, so if I specifically say on a problem use tail recursion, then use tail recursion. Or if I say use an inductive construction approach, then use an inductive construction approach. Otherwise, you can use either technique that is more appealing to you. So Thursday, I talked about tail recursion, the idea that all the computing is done with continuation arguments and there is no processing done when the function returns. It simply returns a value and then you can reuse the stack frame. Not you, but the scheme interpreter can reuse the stack frame. And it's kind of akin to pre-processing a list. You'll see as we get to it why, but effectively what we're doing is we are doing some operation on the first, say, element of the list, taking that result, passing it as a continuation argument to recursively along with the remainder of the list. Whereas inductive construction is more akin to post-processing, meaning you will get a result and then you will do some computation after you have the result. So it is like post-processing because basically you will process the remaining part of the list, get a result for it. So if you have a n+1 item list, you will process the remaining n items first, and then you will take that result and apply the first item in the list to it. So we will show how that happens. So tail recursion is like a pre-order traversal on a tree, and inductive construction is like a post-order on a tree traversal. Okay, so we're going to show you factorial, summing a list, and then quicksort as 3 examples. So inductive constructions lend themselves well to recurrences. Okay, so factorial is a natural recurrence where you have the 2 base cases. So remember with recursion, you're always going to have a base case. So normally, when you write a recursive function, it will be a cond or an if. And the first thing you're doing is checking, do we have the base case? So here the 2 base cases are when n is 0 and when n is 1. And in those 2 cases, we return 1. And then otherwise, we multiply or we compute the factorial of n-1. And once we have the result, we multiply the result by n. So think of this as though we got a list of n numbers where the list is n, comma, n-1, comma, n-2. So what we're doing is we're first applying the factorial to the list consisting of n-1, n-2, n-3. Once we have that result, we're multiplying it by n, which is the first element of our list. Here, in contrast, is the tail recursive construction. So in this case, what we're going to do, so with tail recursion, we're almost always defining a recursive helper function. Whereas with the inductive construction, we often will not have to do a helper function. So it's perfectly okay to have a helper function in your homework assignment. In fact, as I said, with tail recursion, you're almost always going to have a helper function. And so it's a let rec because it's a recursive function. And in this case, tail recursion, remember, is going to be using continuation arguments. So with tail recursion, we're going to be building up the product as we go along. It's going to look more like an iterative version of factorial. And we still have our base cases. So when we get to the case where n is 0 or n is 1, we return the product that we have built up. If we're not yet at the base case, then we multiply the product thus far by n. So that's our continuation. And we decrement n by 1. So this is kind of like saying we're doing a for loop where n is going, or we're doing from I equals n down to 1. And at each point, we are multiplying the product by I. So this is kind of what you're seeing here is the equivalent of a imperative program that is saying for I equals n down to 1. So product, first of all, is equal to 1. And then we're saying product equals I times product. So that's what this tail recursion is essentially doing. Okay, and then after we've defined the recursive helper function, so that was the recursive helper function, we then call fact helper with the product initialized to 1 and n. So we're hiding this fact helper from the user. It's like a nested hidden function. And all the user sees is that they're passing in this one argument. And then we construct a separate recursive function that computes some intermediate results. Okay, so that's our first example. Our second example, we're going to sum up a list of numbers. And I understand that basically what we're trying to do is just simulate the plus operator, because the plus operator in Gambit can already sum a list of numbers. So that's all we're trying to do, is sum a list of numbers. Okay, so again, but now it's a list. So we're taking a list, and this is what you're normally going to be operating with in Scheme. So our first example had a simple number as an argument. The second example is using a list, and this is far more common, that you're dealing with a list argument. So now the base case is when we have an empty list, which is in that case, null will return true. And in that case, the sum of an empty list is 0. So I'm assuming that if I'm given an empty list, the sum is 0. Otherwise, I will add the car of the list to the result that I obtain by applying some list to the remainder of the list. So this is post-processing, because I'm first computing the sum of the remainder of the list, and once I have that sum, I'm adding the car to it to get my result. Okay, so this is inductive, because basically we're building up from the definition of it was 0, and then when we were assuming. So another way to think of the inductive construction, by the way, is to assume, the inductive construction says, I assume we know the answer for all arguments from 0 to n. Now I want to compute the result from n plus 1, whether that's an integer or a list of length n plus 1. It assumes that if it's a list, we're assuming we know how to get the result for any list of size n or less. And now we're going to figure out how to get that result for a list of size n plus 1. That's the inductive construction. Okay. The tail recursion construction goes the opposite way. It says, I am going to start with an empty list. Then I'm going to build a list of length 1. Then I'm going to build a list of length 2. Then I'm going to build a list of length 3, list of length 4, until I get up to a list of size n plus 1. So the inductive approach is saying, okay, I know how to solve the problem. Okay, so let's actually go back. And so the inductive approach says, okay, I can solve this problem for any list of size n or less than or equal to n. And I now have a list of size n+1. So what I'm going to do is I am going to call my function on a list of length n. And what is a list of length n? It is the cdr of my list. And then I'm going to apply the car of the list, which is the n+1st element, to my result. That's the inductive approach. So it says I can solve any problem thus far with that has a list of size n or less. So I'm going to recursively call my function on the cdr of L, because that will give me a list of length n, and I can solve that. That will give me a result. And now I will somehow combine result with the car of L, which is the n+1st element, to get my result. In contrast, the tail recursion says, okay, what I'm essentially going to do is start with a list of length 0. So essentially the tail recursion is more like going to say for I equals 0 to n, build a list of length. Sorry, I can't spell. Length I. And the way it does that is it assumes it's kind of the same way, which is it is it's building it up a list. So it first gets a list of 0, then it gets a list of 1, then it gets a list of 2, then it gets a list of 3. So by the end, it has its list of n+1. So it's kind of going in the opposite direction. Okay, so we look at this. That's what's happening in the inductive construction. It calls SUMList on the cdr, gets that result, adds car to it. Tail recursion says, okay, again, I need to define a helper function. I have the sum thus far and the list. And what I'm going to do is if the list is null, I'll return the sum I've computed. Otherwise, what I'm going to do is I'm going to remove the first element from the list. So the list that I pass to the recursive one is the rest of the list. Meanwhile, I'm going to take the car of the list and add it to the sum thus far. So I'm essentially starting with a list of length 0, adding car to it. Now I have the result for a list of length 1. The second call will create the sum of the first 2 elements. The third call will create the sum of the first 3 elements. Fourth call will create the sum of the first 4 elements, and so on. So the way that these two are operating is fundamentally different. In fact, let's look. What I'm going to do now is trace these two. So I'm going to start with this inductive definition. Put it in sumlist.scm. I'm going to load sumlist. And I'm going to trace sumlist. And now we're going to do sumlist on 4, 5, 8, 9. Okay, and you can see what happens is the first thing it adds actually to the sum is 9, which is the last element. Then it ends up adding 8 to get 17. Then it ends up adding 5 to get 22. And then it ends up adding 4 to get 26. So the inductive way of doing it actually ends up going from back to front. Okay, now let's look at the other approach. So we will redefine it. This way. And we'll just reload that function. And I have to reissue the trace. When it changes, you have to, apparently it loses the ability to trace. So now we'll do some list on that same list, which was 4, 5, 8, and 9. Okay, and the reason I got back 26, unfortunately, is because it, I have to figure out how to trace that recursive version. I trace the recursive version. Let me try this. This may or may not work.
Did you simply trace some list helper?
Pardon?
Could you simply trace some list helper?
That's what I'm going to do. I think I can say trace some list helper here. I think this will work. Thank you. So we'll try that. We'll reload. So I'm using the arrow keys to get previous commands. There we go. So you'll see here, sum list helper added 4 to get this sum. Then it added 4 and 5 to get this sum right, this sum right here. Then it added 8 to this 9 to get 17. And finally, it added 9 and 17 to get this 26. So the tail recursion version is going through it from front to back, whereas the inductive did it back to front. Okay. Okay. So actually, we don't have time to get to quicksort, which is our biggest one. So we will resume this discussion on Thursday, and we will go over how to create an inductive construction of quicksort and a tail recursive definition of quicksort on Thursday. Then also in our list of coming attractions for Thursday, we will go over a more complicated example, which is we will be going over a simulation of a deterministic finite automata to show you a more complicated scheme program, because our programs are going to be fairly simple. And finally, we will be going over evaluation order, although I might flip-flop it. I might go over higher order functions on Thursday and defer evaluation order till next Tuesday. If so, I will let you know. Final thing, no quiz today. So there is no quiz today. So don't worry about doing a quiz today. Okay. So with that, I will let you all go.